Hi, I'm Amy. This video covers a couple of strategies that'll come in handy for you if you're working on a limit that turns out to be an indeterminate, 0 over 0, and factoring and reducing just isn't working for you. Taking a look at this function right here, as x approaches negative 2, we can see that the denominator goes to 0 because negative 2 plus 2 is 0. And in fact, the numerator does also. Negative 2 plus 6 is 4, square root of 4 is 2, 2 minus 2 is 0. 0 over 0 tells us nothing. We don't know whether the limit exists or not. This is called an indeterminate case. And so we have to try something else. What we're going to do here is called using the conjugate. Your experience with conjugates might look something like this. A plus b times a minus b. They're practically the same expressions except for one has a plus in the middle and one has a minus in the middle. When we multiply those out, you get a squared minus ab plus ab and then minus b squared. And the thing you'll notice here is that the two middle terms add up to 0, and we're left with a squared minus b squared. Now we're going to use that concept to help us simplify our limit. What we're going to do is we're going to multiply our limit by 1, but that 1 is going to be in the form of root x plus 6 plus 2. Notice that's the conjugate of the numerator of the original function over itself, root x plus 6 plus 2. So as we start multiplying this out, what you're going to see is that because we're multiplying conjugates together, those two middle terms are going to fall out, are going to add to 0, just like they did over here. So we've got root of x plus 6 times itself. I'm going to write that as root of x plus 6 squared. We have plus 2 times the root of x plus 6. We have minus 2 times the root of x plus 6. And we have minus 2 times 2, which is minus 4. I'm not going to multiply out the denominator because you'll see as the problem progresses that it's actually just not necessary. So in simplifying this, we get the limit as x approaches negative 2. Still writing that down because we're still looking for the limit. This piece simplifies to x plus 6. These guys add up to 0, and we have a minus 4 on the end. And I'm going to leave the denominator still just as it is. All right. And now you see that the numerator is x plus 2 also. And because of that, this x plus 2 over this x plus 2 equals 1. So we're left with 1 over that square root of x plus 6 plus 2. Now we can try direct substitution. We have 1 in the numerator, and the denominator is root of negative 2 plus 6 plus 2. That's root 4. Root 4 is 2. So we have 1 over 2 plus 2. We have 1 over 4. That is our limit. This is a pretty typical kind of problem you'll see in AP Calculus, and most of the time this conjugate method is exactly what it takes to solve it. For our next example, we're going to look at the limit as x approaches negative 7 of x plus 7 over the absolute value of x plus 7. Hopefully you can see that as you plug in negative 7, you're going to get 0 over 0, which is another indeterminate, which means we need to figure out something else we can do. If you think about this problem graphically, plug in a number like 0. If I plug in 0, I get 7 over 7. Well, that's 1. If I plug in 1, I get 8 over 8. That's also 1. In fact, if you plug in almost any number, you're going to get 1. The kind of cutoff point for that is when you get to negative 7. So if we plug in negative 6.9, we're going to get 0.1 on the top and 0.1 on the bottom. That's 1. So as long as the values match, as long as they're both positive, you're going to get 1. In fact, our limit as x approaches negative 7 from the right-hand side, from above of our function, is going to be positive 1. Where things change is when we're coming in from the left-hand side. That limit as x approaches negative 7 from the left-hand side is going to be equal to -1. Why? Well, if you think about plugging in a value like, let's say, -8. If I plug in a -8, the numerator, -8 plus 7, that numerator would be -1. And then that denominator, -8 plus 7 in absolute values, goes to +1. -1 over +1 gives me this -1. So from -7 and everything below that, we're going to have an output value of -1. And since the limit coming in from the left is -1, and the limit coming in from the right towards -7 is +1, those two limits aren't equal to each other. Therefore, the overall limit does not exist. The right-handed limit exists, the left-handed limit exists, but because they're not approaching the same numeric value, the two-sided limit does not exist. Here's a couple of similar problems we can use to practice these methods. On the first example, you see if you plug in 0 for h, you would get 0 on the top and 0 on the bottom. So let's go ahead and use that multiplying by the conjugate idea. I'm going to multiply by root of h plus 9 plus 3 on the top and bottom because we had a minus right here. As we multiply these out, we get h plus 9 plus 3 times the root minus 3 times the root. Those add up to 0. And then minus a 9. And in the denominator, I'm going to leave it just as it was. Of course, 9 minus 9 add up to 0. I also see I have an h over h, which reduces to 1. And now, if we plug in that 0 for h, we do our direct substitution, we get 1 over 0 plus 9, so root 9 plus 3. Well, root 9 is just 3, so this is 1 over 3 plus 3, or 1/6. On this last example, we're looking at the limit as x approaches 3 from the left. So think about a number like, I don't know, what's something to the left of that? How about a number like 2? So if we have 2 minus 3 in absolute values over 2 minus 3, I get -1 in absolute values on top. I get -1 on the bottom. I get 1 over -1. We get -1. So it turns out if you pick any value up to, but not including 3, your output value is going to be -1. So when you look at that graph and you look at when the x values are getting closer and closer to 3 from the left, you'll see that the output values are consistently at -1, which means our limit is -1. Remember, limit is where is the graph heading? Well, the graph is heading pretty consistently. It's at -1 and it's not deviating from that. It doesn't matter that there's a hole there. It doesn't matter that our function is undefined there. And just for your information, the rest of the graph would have the output values above 3 at +1. This is a pretty typical AP calculus problem again, and one of the best ways to think about it is just to kind of envision the graph and go from there.